So today we're happy to have Adam Levine from the Institute for Advanced Study here. He's gonna give a talk about probing strings with quantum extremal surfaces. Thanks so much, Adam, for accepting, and please go ahead.
Yeah, thanks. Thanks for the invitation. Hopefully someday I'll be able to come visit in person at Purdue. So yeah, I'm talking about some work in progress with Ven and Tom Faulkner. Ven is a grad student at Berkeley, but he's coming to the Institute this coming year. We have sort of been thinking about, by the way, is my audio, everything is okay? By the way, just let me know if you can't hear anything.
That's perfect, thank you.
And obviously stop questions if I'm stop me with questions if I'm going too quickly. So we were trying to understand better if the nature of quantum extremal surfaces change when you include finite or non-zero string length corrections in the bulk. So I'll explain, or I'll give a little brief review of what quantum extremal surfaces are, but there have been a lot of recent developments related to computing the page curve in black hole evaporation using quantum extremal surfaces. So it's clear that they're an interesting construction that's going to teach us a lot about quantum gravity. And we wanted to understand if their nature changes at all, or what corrections there are to the nature of a quantum extremal surface. So in particular, I have this picture here, which I'll explain better. But the rough idea is that this dot here represents the quantum extremal surface for some boundary region. And there's this idea of entanglement wedge reconstruction, which is that you can reconstruct everything which is bounded by the quantum extremal surface, or to one side of the quantum extremal surface. And this idea of entanglement wedge reconstruction is key for understanding the page curve. But there's this interesting thing that the position of the quantum extremal surface is intimately tied to the scrambling time, which is a notion that comes from out of studying quantum chaos and the boundary theory and computing so-called out-of-time ordered correlators. And we were interested also what happens for theories which are given which are not maximally chaotic. So maximal chaos is associated with having a semi-classical gravitational theory in the bulk dual. And we were wondering, what does this mean for the quantum extremal surface if you have a boundary theory which doesn't have maximal chaos but has submaximal chaos? So it still has an exponentially growing out of time ordered correlator, but it is not growing with the maximal Lyapunov exponent allowed by the chaos bound. So if none of that really made sense, I'll hopefully try and explain in a bit. But that's the basic idea. Does the nature of the quantum extremal surface change? Okay, so the outline is I'm going to explain the setup, which should explain the picture that I just drew a bit better, and then I'm going to explain some quantum information ideas that we're going to use to compute various measures of when a particle is in the entanglement wedge or not. And that will lead us naturally to considering a specific modular flowed correlation function, which was used in the proof of the quantum null energy condition. And we'll try and compute that correlator in a limit that hasn't been computed before, namely this Regge limit, which is a specific kinematic regime for correlation functions, which I will also explain. And we'll compute it in a particular limit for certain regions. We'll need to compute modular Hamiltonians in a certain limit that hasn't been computed before, or only partially computed. And then we'll compute these quantum information measures explicitly. And then I'm going to comment on some bulk. What these are all boundary quantities computations that I'm doing, and I'm going to comment on their bulk interpretation in terms of quantum extremal surfaces. All right, so let me tell you the setup. So the main idea is the following. Here I've drawn a picture which is in higher dimensions. I'll talk about a lower dimensional example for most of the talk, but in the back of your mind, you should keep this higher dimensional picture in your head. The idea is that I have a CFT on the cylinder, Lorentzian cylinder, and it's dual to some, to some vacuum ADS spacetime. And I'm going to pick some regions on the boundary. The region that I'm going to be interested in is a disconnected union of two disconnected spheres. In the picture I've drawn, they're intervals. So the one interval is L. I'm going to call it capital L for the left interval. And then the other interval, I'm going to call I. Okay. So the union of Li is some region on the boundary, and it has some entanglement wedge in the bulk. The entanglement wedge associated to L is just this wedge whose entanglement surface is given by it lies on the ADS Rindler horizon. It's sort of this bifurcation surface for this hyperbolic black hole in the bulk, but it lies right on the Rindler horizon. Now, if you add to L this interval I, there's a quantum extremal surface somewhere in the bulk, which I've denoted quantum extremal surface of Li. And because of entanglement wedge reconstruction, it needs to be strictly larger. This region in the bulk needs to be strictly larger than the quantum extremal surface just for L. So there's some surface which is out here, which can be found by extremizing the following quantity. You take a surface, you compute the generalized entropy for that surface. So that means A over 4G of the surface plus the bulk entropy of the quantum fields associated to some entanglement wedge, E of Li, okay? So now you extremize over all possible E of Li, this S-gen, and the area here is the area of this surface, suitably, cut off. There are some infrared divergences, blah, 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 but hopefully this is sort of familiar to most of the people in the audience, but if not, the idea is you just take this quantity, this generalized entropy, and you extremize it over all possible dashed red lines, okay? Now, because of the symmetries of this problem, you only actually need to, if I and L lie on, a constant time slice on the boundary, then you can just extremize only over surfaces that lie in this constant time slice in the bulk. And you'll find, we do this in the paper and other people have done this, you'll find that there is a surface which is slightly out from the ADS Rindler horizon. And so the quantum extremal wedge, or the entanglement wedge, includes strictly more in this case, okay?
So
and we want to...
Question, yeah. Adam? Sorry, yeah. I'm a little confused. So what is E of Li?
E of Li in this picture would be everything bounded by, in this picture would be everything bounded by this dotted red line, union a little entanglement wedge here. So that would be E of Li. Well, or maybe it's causal completion. I'm being a bit sloppy in my language there, but it's the causal completion of that codimension 1 region that I've shaded in.
And the A is A of the boundary of this E of Li?
A of this dashed red line, yeah. A of dashed red line union this little piece here.
Both of them, okay.
Yeah, sorry, both of them.
Yeah, okay, good.
Yeah, sorry. The reason I have ignored this contribution here is because, as we'll see, I'm going to take the small I limit where this region is sort of unimportant. But yes, in principle, you need to extremize both positions of these surfaces. So in general, this is a hard thing to do. We'll particularly because this quantity here is difficult to compute, but this bulk entanglement entropy. It's the, S bulk, I should say, also for people who don't know. It's the entanglement, it's the entropy of the reduced density, the von Neumann entropy of the reduced density matrix on this region, which in the bulk of the low energy quantum field theory in the bulk spacetime.
So sorry, quick question.
Yeah.
As you shrink the region I, doesn't that QESLI become the ADS Rindler?
Yes, correct. It limits back to the ADS Rindler horizon. Mm-hmm.
But this is a little bit of a tricky thing because when you shrink AI, the area term that you're talking about, that still always is infinite, right? It is a
You
little bit
have
of a
to
singular
introduce
limit.
some cutoff. That's right. Mhm.
Okay, thanks.
Are there any other questions about this setup? In particular, anybody who doesn't know much about quantum extremal surfaces that needs more clarification.
Yeah. I have one question. What is the connection between L and I? I just don't quite see
What is the connection?
Yeah.
There's no explicit connection. I'm just picking my boundary region to be the union of these two regions on the boundary. So L is a boundary region, so it's some boundary sphere that takes up half the CFT, and I is some other sphere. I'm going to take it to be small, but the boundary region I'm interested in is the union of L and I.
Okay. So basically, they are arbitrarily chosen, right?
Pretty much arbitrarily chosen.
Okay. Thank you.
The reason now I'm going to explain why I'm interested in these. So the reason I'm interested in this is because I'm going to take the small I limit, where the position of this quantum extremal surface in gravity is actually, well, in the model that we're going to consider, which is a slight variation of what I'm talking about right now, but it's going to be computable in that limit. But the basic idea is I want to come up with a boundary quantity that probes the position of this quantum extremal surface. Okay, so the way I'm going to do that is the following. I'm going to consider states, which I call psi, which look roughly like, I take an operator, phi right. So capital R is going to be the complement of L. It's the complement of L, so it's this whole boundary region. And little r, excuse me, little r is the complement of Li, right? So it's the union of these two intervals in this picture. Does that make sense, everybody? So what I'm going to do is insert an operator, phi capital R, which will have support over this whole right region. And I'm going to insert it at some boundary time, and I'm going to move it into Euclidean time a little bit. The reason I want to move it into Euclidean, so I'm going to evolve it with respect to the boost generator of this right ADS-Frindler wedge, which on the boundary is just a conformal boost. I'm going to evolve it back in time, okay? And what this is going to do is insert this particle near the boundary. So I'm going to include in the limit where I don't include any Euclidean smearing. This is a non-normalizable state. It creates an infinite energy excitation. But if I include a small amount of Euclidean time smearing, then this operator is actually the state is normalizable and has finite energy, basically because the Euclidean time smearing suppresses high energy modes. And the bulk picture is that a particle very near the boundary is going to fall into the bulk, and on this time t equals 0 time slice, it has some support, which I've represented by this blob here, okay? So there's some support for the excitation in the bulk, and as I move back, the position of this excitation should move deeper into the bulk, roughly speaking. So as I move my excitation farther and farther back, which is this picture, eventually the excitation will have some support which crosses the quantum extremal surface. So in particular here on the left, this excitation is mostly supported in the entanglement wedge of little r. The entanglement wedge of little r is the complement of the entanglement wedge of Li. So it's everything that's not, it's all of this region here.
Sorry,
right?
there's one, Adam.
Yeah.
I'm confused about one thing. So are you thinking of, the picture you're drawing seems like you're literally thinking of putting a local operator.
I'm inserting a local operator into Euclidean time on the boundary and letting it fall into the bulk. So yeah.
The problem I have is that if I take an operator phi of r, and that's in the right wedge, right region, if I evolve it with a teeny tiny Euclidean time amount, I'll actually have support on left as well, unless I tune this operator, smooth it further. So I have to smooth it further a little bit in boost time.
Yes, I agree that strictly speaking, this operator, when I do this Euclidean evolution, will have some support on big L. The way we should think of this Euclidean time evolution is for small little delta, which is the amount of Euclidean time evolution. It's basically equivalent to doing a smearing in Lorentzian time of this operator, up to little delta.
Perfect. Okay, that I'm perfectly happy with.
Okay, so I think what I really have in mind is doing a Lorentzian time smearing.
That's very fair. Good, thanks.
But it's hard to work with, so I'm going to do a small amount of Euclidean time evolution. Okay. So our goal here is to sense this transition represented in these two pictures, where the excitation that's on this t equals 0 slice is mostly contained in little r, and then it moves into being contained in the entanglement wedge of Li. What that means, so what we've learned, for those of you that don't know, is that when an operator in the bulk is mostly contained in the entanglement wedge of a region on the boundary, that means that it is reconstructible from that boundary region. What that means in practice is that there is an operator, or strictly speaking, a unitary supported on that boundary region, which can create or destroy that excitation, right? So in this picture on the left, there should be an operator supported according to entanglement wedge reconstruction. There is an operator supported entirely on little r, which should create this blob here at the time t equals 0, a boundary operator. Once it's crossed into Li, into the entanglement wedge of Li, there should be a unitary supported entirely on L union I that can create or destroy this blob, okay? So what we'd like is a boundary quantity which senses that transition. So that's the goal. This picture is good in any dimension. I should say, sorry, we're also working in the limit where lambda is small, so that's just going to help us in computing some of these quantities. This picture, this state you should think of as I've inserted a unitary e to the I lambda times phi, where phi is smeared a little bit in Lorentzian time, and I'm expanding, and I'm acting this unitary on the vacuum and expanding in small lambda. Okay, so then I should, to leading order, end up with a state like this. Now, in any dimension, that picture that I just showed you works in any dimension, but things are simpler if we have 2D CFTs for various reasons, which will become apparent. So what I would like to do is introduce this other model, which was first discussed in two nice papers by Almeri, Mahajan, Maldacena, and Zhao. Sorry, this is not a Y, this is a Z. Ying is her first name. In these nice papers, they introduced an interesting model, which is the following thing. So we have become, in the last several years, used to this idea of ADS2 CFT1 or nearly CFT1 holography, which is a low dimensional version of ADS CFT. And the idea is that in such a setup, you have 0 + 1 dimensional quantum systems, which I'm going to imagine are living along these lines here, these vertical lines, that are dual to an emergent ADS2 geometry, which is going, or ADS2 black hole, which is this region in here. And their low energy theory is described by JT gravity in the bulk. And what we're going to do is couple these theories, which live here, to a flat space bath. So there are really two, we should really think of what I'm drawing here as having two descriptions. So what strictly speaking, what I've drawn here is a semi-classical description where you have quantum fields, low energy quantum fields, coupled to JT gravity. And we're coupling it in such a way that JT gravity, so G Newton is not 0 here, or it's greater than 0 here. It's still small. I'm going to assume that G Newton is very small, but here out in this region, G Newton is 0. So there's sort of a domain wall of some sorts that sits right here and lets excitations from this non-gravitational region enter into this gravitational region. So as I said, this is a semi-classical description of some microscopic description. And the microscopic description looks like this. It's baths, which are 1 plus 1 dimensional theories coupled to a quantum dot, or a 0 plus 1 dimensional quantum system. And the bath this is a bath. And there's another one over on the other side as well. So these are both 0 plus 1 dimensional quantum systems, and they share some entanglement, right? And the sharing of entanglement produces this thermal field double-like space-time in this semi-classical picture. So there are quantum fields here which interact with this 0 plus 1 dimensional quantum dot. They, excitations can come in and scramble a bit and then come back out. And all of that has a dual description, which is given by this semi-classical picture, where excitations from the bath can just move from the bath into the gravitational region and sort of sail through. Now, there's some subtlety, which I won't get into, about coupling the two regions, moving from a G Newton equals 0 to a G Newton not equal to 0 region. But the rough picture is that excitations from the bath just sail right through, okay? And we can pick in this UV description, or in this microscopic description, I should say, we can pick a region, okay? That's the analog of picking a boundary region in the previous slide. So the region that we'll be interested in is the whole left bath plus the quantum system, union and interval in the right bath. So I is here and L is here, okay? In the semi-classical description, L is here, I is here. And now these two regions together include some reconstructible region in the emergent gravity description. And L on its own can reconstruct everything up to the bifurcation surface of the black hole. So it's natural to think that L union I includes more. So its quantum extremal surface goes all the way into the right exterior of the black hole. Just as in the previous picture, the quantum extremal surface of Li moved into the right Rindler wedge. So this is really just a low dimensional version of what I was discussing above. So the idea is that we're going to take this small I limit, and we're going to insert an operator which is an operator in the UV description. It will be an operator in this quantum dot. We're going to insert something here and let it fall into the black hole. And eventually it's going to cross this quantum extremal surface and enter the entanglement wedge of Li, okay?
Sorry, a quick question.
Yeah.
So this perturbation on the quantum dot on the right side,
yep.
You're just drawing how it propagates into the bulk, but it will propagate to the right path as well, right?
But those, well, for simplicity, we're going to assume that the bulk theory is basically like a generalized free field coupled to JT gravity, a generalized free CFT basically. So it obeys Wick contractions, but it's but the field dimensions don't, can be general. And we're just going to focus on chiral operators, so we can kind of get around that issue.
I see. So you pick it to be chiral. Thanks.
They need to be chiral, but I should say that they don't. Sorry, we're going to take them to be chiral just for simplicity, but I should say that even if they weren't, the dominant effect, if you inserted an operator, say a large mass operator, would be for it to fall into the black hole. There should be some subleading effects, which are subleading in actually, yeah, they're chiral. Let's just put it there. So the model we're going to take is JT gravity plus stringy corrections, and I'll explain below what I mean by that. We're not working in any specific model of string theory in 2 dimensions, but we're going to correct various formulae in a way that is consistent with what string theory does in higher dimensions, what we know string theory to do in higher dimensions. Okay, so this is the setup. That will be sort of relevant throughout the talk. So if you have any questions about this, probably now is the time to ask. All right, so what we want, just to reiterate, is some measure of when this excitation that I've drawn here leaves the entanglement wedge of little r. So I should say the entanglement wedge of little r is everything other than the entanglement wedge of L union I. So we want to measure when this excitation leaves the entanglement wedge of little r.
Sorry.
Yeah.
Quick question.
Yep.
So you are working some sort of a probe approximation where the propagation of this particle into a bulk does not change the boundary, this quantum dot.
I will explain,
right?
yeah, correctly. I will explain, sorry, that is correct. I will explain where the probe approximation comes in later. But yes, we are, so for example, if this excitation fell in and it could affect the position of the quantum extremal surface, for example. We don't want to do that. We just want to use this as a probe of the background quantum extremal surface for the vacuum.
Sure, thanks.
Yeah. But actually, well, it's difficult calculationally to change to compute what we're going to compute out of the probe approximation, but it's straightforward in principle. I can explain what you would need to do to account for those effects. Okay, so I want a quantity which senses when this transition happens. So what's a good quantity for this? So this is when I'm going to introduce some information measures. So when is the excitation reconstructible from Li? So I said it's reconstructible from Li when there exists a unitary supported on L union I, which removes or creates this excitation, right, in the bulk. So what we want is we have our state psi, which has this excitation somewhere in the bulk, and we have the vacuum, the state without the excitation, and we want to look at all the possible unitaries, which could get close to turning the vacuum into this state psi. If there does exist a unitary supported just on Li, then this quantity is supremum, which is called the fidelity, or it's the quantum fidelity. This quantity should be close to 1. So this fidelity is exactly the measure that we're looking for. It's 1 if and only if the 2 states agree exactly. So one comment about the fidelity is that because of this supremum, the fidelity just depends upon the reduced density matrices in the region little r. Okay, the reason for that, which is why I've said it depends on little r. The reason for that is that all purifications of reduced density matrices on little r of the same state are equivalent up to action by unitaries on the complement region. So when we do this supremum, we're just removing the dependence of this purification on the complement region, right? So this actually, there is a formula for this, which we will come back to, which is just in terms of these density matrices. Now, clearly by this formula, the fidelity is bounded between 1 and 0, and it's 1 if and only if the states are exactly equivalent on little r. So it's 1 if and only if it's perfectly reconstructible from the excitation is perfectly reconstructible from L union I. So what we would like to do is compute the quantum fidelity for these states psi. And this is where the small lambda limit will help us. So these states are, the fidelity is hard to compute explicitly in general, but we can make headway if we take the small lambda limit and expand perturbatively. And what you find is that 1 minus the fidelity is equal to, it doesn't have a linear in lambda piece because you could just change the sign of lambda and violate these bounds here. But it has an order lambda squared piece, and it's proportional to what's called the fidelity susceptibility of these 2 states. Okay, and this quantity is more computable. And it's what we will compute, okay? Unfortunately, this is a bit technical, and there are simpler. Even computing this fidelity susceptibility down here is a bit technical, and there are simpler quantities that we could compute that illustrate the main aspects of the transition.
Sorry, quick question.
Yeah.
Adam. I think I'm confused about something very simple. If you scroll up a little bit.
Yeah.
So you're saying that the excitation is perfectly reconstructible from Li if and only if the reduced density matrix on little
Yes, on
r.
little r.
Never mind. Okay, sorry. Little r. Okay, thanks so much.
Sorry, so here are some facts that I already said in words, which is just that the fidelity is only dependent on the purifications. Sorry, on the reduced density matrices in little r, because all purifications are equivalent up to unitary action on Li. And there is a formula for the fidelity, which is just in terms of these density matrices. It looks a bit imposing, but when you can expand it in the small lambda limit, where the state psi is close to omega, you can do perturbation theory and just expand this, and we will do that later. But as I was saying, even expanding this gets a bit technical. So what we'd like is a quantity which is simpler to compute, but illustrates the same features. And
Sorry, Adam.
Yep.
Can I interrupt you? Sorry, I apologize for.
No. It's good.
So if you the statement you said about the if and only if statement that you said that rho of r equal to omega of r or whatever you called it is if and only if f is equal to 1. For this statement, you don't need this perturbation to lie inside R, right? It's basically any unitary that acts on the Hilbert space. It will generate for you a new vector. There will be new reduced density matrices, and then that if and only if statement will hold, and it's fine.
Sorry, I'm the if and only that if and only if statement is true. This if and only if statement is true totally generally. You don't need the statement. You don't.
Yeah. So what I'm saying is that you said you wrote u of I see. Yeah, that's right. Yeah. Okay, thanks so much.
Yeah, this unitary is supported in Li, not in little r. Yeah, so it's confusing. The notation is a little bit confusing.
I guess I meant that you don't need the vector psi to be generated from the vacuum using a unitary that's localizable on capital R.
No, you do not. That's right.
Okay, thank you.
Sorry, just to see a follow. So this will be a function of time, like you insert phi r in the path, and as you evolve, this f goes from 0 to 1.
Yep. I'll show you plots at the end. That's exactly right. Yeah. And you're trying to look at we're trying to understand the transition where it goes from being some small thing to close to 1.
Oh, thank you.
Yeah, so everything is a function of this TR here, and delta actually, but okay, good. So the quantity that's a little bit simpler to compute is the following. It's related to the relative entropy, which is the fidelity is a measure of the difference between two reduced density matrices. And the relative entropy on little r is just another measure. It has this form in terms of the reduced density matrices. And it's a measure of distinguishability. So you might expect that when the relative entropy is large between two reduced density matrices, then the excitation is well localized in little r. And when the relative entropy is small, you'd hope that the excitation is well localized in the complement. Just intuitively speaking. That intuition can be made slightly more rigorous just by noting that there's actually a bound between 1 minus the fidelity and the relative entropy. So when the relative entropy is small, this quantity is close to 0, and that means that the fidelity needs to be close to 1. So indeed, when the relative entropy is small, the fidelity needs to also be close to 1. So for pure states, you can write the difference in relative entropies. Okay, so the relative entropy for the region R minus the relative entropy of its complement, Li, as the expectation value of log of this operator, which is really log of sigma omega minus log of sigma sub R minus log of sigma sub Li. And we're computing this in the state psi, right? So it's an expectation value of this operator in the state psi. I'm using this delta notation just because it's slightly simpler. Delta is like a generalization of the boost. So if little r were a Rindler region, delta would generate, or delta to the IT would generate boosts. But because these regions are unions of disconnected intervals, that's not true anymore. But you can think of these as sort of being generalizations of boosts. So in these states, we can compute this quantity, log of delta omega r, by using this differentiate definition. So you can compute the expectation value of this delta omega to the IS and compute its derivative. Okay. Does this make sense to people? So I've used purity here to cancel off. This quantity is equal to the same thing where I've replaced little r with Li. This is a fact that for pure states, the von Neumann entropy is equal, for the von Neumann entropy for a given region is equal to the von Neumann entropy of its complement. So when you take this subtraction here, these terms cancel off and you're just left with a difference of these terms, okay? And that's exactly what this is. Why do I want to compute this expectation value of what I'll call the full modular energy? The reason is when the excitation is localized well in little r, this difference here you'd expect to be positive and large and positive. When it's well localized in little Li, the relative entropy for little r you'd expect to be small, so this quantity should be negative. I should mention here that I'm using the fact that the relative entropy is always positive, so SREL. This is a fact you can prove, and it's SREL equals 0 if and only if the two reduced density matrices are equal. Okay. So when this quantity here is positive, you'd expect the excitation to be more well localized in little r. When it's negative, it's more well localized in Li. Does that make sense to people? This is not entirely rigorous. The rigorous thing to do is compute the fidelity, but this is a simpler quantity to compute.
A question, Adam.
Mm-hmm.
So fidelity is symmetric in the two states, but relative entropy is not.
Correct.
So,
yeah.
So fact one is true for either order of relative entropies.
Yes, that should be true. Yeah. That's
okay. And the fact two that you're using particular relative entropy. If we use another one, are we gonna get something stronger than what you're gonna show us, or
if we use a different relative entropy?
Yeah, like instead of S sigma rho, or like change the order of the states.
Oh, I see what you're saying. Yeah, in principle, you could get you could get a stronger, or you could get a different bound. Yes.
All right, thanks.
The one I will compute is the one where the vacuum is in this right slot.
But sorry, in the probe limit, you're supposedly doing some lambda expansion, and that's just a Fisher information, so it doesn't.
And that is symmetric. Yes, right? Yes. Sorry.
Okay.
You're right. Yes, that's correct. Right. Thanks, Nima.
All right, thanks.
But in general, yeah, if you're not working in that limit, in general, you could get two different bounds. Okay, does this make sense to people? All right, so our goal then for now, before I come back to the fidelity at the end, our goal is just to compute the expectation value of this modular evolution operator in the psi state, which is equal to this. You can change the label here of which region you're computing to the complement at the cost of introducing a minus sign up here. Right, which is what I've said here. So the state, just to remind you, is this near vacuum state. So you can expand here And the leading term is an order lambda squared term up to terms that are independent of S. We're going to use this differentiate dictionary and differentiate definition and take an S derivative near S equals 0. So these terms will all drop out. So just up to terms that are independent of S and higher order in lambda, you just get this expectation value here. And so we need to compute this guy. Okay, how do we compute that? The way to compute it is, or one way to compute it, is to relate it to the following correlation function. So this correlation function is a correlator. So it includes an operator phi left, which is inserted on the left. I should say these labels here, L and R, are a bit redundant. I'm just trying to make it clear that this is an operator inserted in the left. This is an operator inserted in the right. And this is these are just modular evolution operators for the region L and the region Li. Okay. How is this? Why? If I can compute this, I can get to this quantity up here just by doing analytic continuations. So how do I see that? Well, this operator here, this modular evolution operator, is just a boost generator. It effectively just shifts T left. Okay. That's because L, remember, L is just this simple Rindler-like region, and so its flow, its modular flow, this guy just generates boosts. This is what I was saying earlier. This thing is a bit more mysterious, but we'll try and get a handle on it in a bit. But the point is that you can compute this correlation function and analytically continue in, say, T left and T right and get to this quantity. The particular analytic continuation is maybe not important for the talk, but just know that I'm really just going to compute this thing and then analytically continue it and get what I want. Okay. So this correlation function is interesting. It's been computed before well, a similar correlation function has been computed before in other contexts. I call it the QNEC correlation function because it's similar to the correlation function that was considered in the original proof of the quantum null energy condition. And it has an interesting interpretation, which I will get to, in terms of scattering this excitation phi right off of a shock, which appears in the bulk due to this modular evolution. Okay, so now we want to compute this thing. And in general, this correlation function is hard to compute. The reason is that Li, the modular flow of Li, is just not geometric in any way.
Sorry, Adam.
Yeah.
I'm a little bit confused about the analytic continuation comment.
Uh-huh.
So what you want to compute is a function of S, and you have these delta fudge factors in there. Now, now you introduced a modular flow of L for the same value S. That's a little bit, I'm a little bit confused.
Sorry.
So that S is to offset TL and TR, right?
Sorry, which the S here?
The delta, the guy next to the left of it. That is to offset T left and T right, right?
I would just say it slightly differently. I'm gonna just compute this thing because it's like yes, but let me just say it slightly differently, which is that I'm gonna compute this correlation function and then undo this offset here to get back to what I want. So I'm undoing the offset here. So in this T left, I set it to minus T right. I have to. This is a left operator, so I have to move it around the thermal circle. So this is this minus I pi. I'm moving it around in Euclidean time. I'm adding to it some I delta so that I can introduce these factors here.
Yeah, no, I understand what the calculation that you're doing. I'm just trying to see if there is a basic lesson to learn here, why that quantity you're computing is easier than the original one.
It's not, it's just its interpretation is a little bit clearer, so I like to think in terms of it.
Okay. Okay.
But if you don't want to think in terms of it, then that's fine. Just that I want something that when I goes to 0 is S independent. That would be nice. Because I'm going to take the I goes to 0 limit.
But it won't be S independent because you have T left and T right that will
Yeah. I just like to
depend
think
on
in terms.
S.
Yes, it's all. I'm not sorry. I shouldn't have tried to make this seem like I'm doing something deep here. This is just a rewriting that's helping me think about it.
Okay, thank you.
All right, so we're trying to compute this correlation function. So how do we compute this correlation function? Well, the way we do it, first, as I said, in the general Li, limit, this is not computable, except in very special theories like free fermion theories. It's exactly computable, but other than that, it's not computable. So we're going to take the small I limit to make it more tractable. Okay, this is an idea that has been explored before by Egon and Faulkner and also others. So in terms of reduced density matrices for the vacuum, I can rewrite these full modular evolution operators in terms of reduced density matrices, and I'm left with this correlation function. So what I'd like to do is compute this guy in the small I limit. So in the small I limit, what this looks like is just it just factorizes because there's no, in the small I limit, there's not enough entanglement between I and L, so these just factorize. But the leading correction looks like some operator, which takes the form e to the minus I, the change in the modular Hamiltonian. So HLI is the modular Hamiltonian for rho Li, and HLI takes the form, sorry, this is a bit messy, HLI takes the form HL tensor HI plus delta HLI, okay? So if you then plug this into here and expand using Baker-Campbell-Hausdorff, you'll get this time-ordered exponential here, where the time ordering is with respect to flow by this factorized density matrix. But the point is, well, the main point is that this correlation function after using BCH is just given by this, okay? So there's some integrals here from 0 up to S, so the S dependence is still there. And times these time-ordered exponentials, okay? I've just used the fact that the modular Hamiltonian is close to this factorized one and then use Baker-Campbell-Hausdorff.
Sorry,
Yeah.
The statement that ULI is almost factorized, is that a boundary statement or a bulk statement? How do you justify this?
It's a boundary statement, right?
Is there a few, like, what is the physics of this? How do we know?
Yeah, the reason you might expect this is just because, so in a CFT, which is what we're assuming that the bulk fields are in this setup here, in a CFT, this limit, oh, excuse me, sorry. This limit is conformally equivalent to a limit where you keep the size of I fixed, but you move it off to infinity. Okay, so you make the separation between these two regions infinite.
So is it, I guess I was asking, is this based on the fact that the 4-point function of 2S operator is cluster?
Yes.
Okay.
Yeah, this is like, yeah, that's exactly right. So how we're going to compute this is we're going to compute this change in a second, or I'll explain how it's computed, and that's exactly what we're doing.
Because you expect, oh, I see. Thanks so much.
Okay, good. So the point is, I'm going to compute this at well, at large n. So and small I, okay, which is equivalent to this large distance limit, where L and I become separated very far. Okay, so if I could compute delta HLI, then I could plug into this formula and try and compute this correlation function. The reason, I mean, this looks maybe a bit imposing. The reason you might think that this is computable is because similar types of correlation functions have shown up elsewhere in the study of quantum chaos, which I will explain in a moment. but for a large N theory, you would expect that the because of factorization, basically, you'd expect that this HLI takes the form of just bilocal integrals of operators over L and I. Plus, there will be subleading and end corrections, but let's ignore those. Okay. So to leading order, what we would like to find is just this smearing function here, basically. So I'm going to call delta L the size of I, and 1 over R is the distance between L and I. Okay. So we can actually compute this function to leading order. This function, I should say, has been computed for free fermion theories in 2 dimensions by various other people. So it's computable in various regimes, but the basic idea is that you should think of this as like a bilocal operator. Okay. And there will be terms which are like, oh, so what is included in here is stuff like O times F integral plus integral, higher orders, but those will all be suppressed in the 1 over N. So the leading thing is just a bilocal integral. So how do we do it? So our goal is to try and compute this function. What we do is, well, briefly, we should say that in this limit, there's an SL2R transformation, which maps the interval I to L and L to I. There's a bijection between the 2 intervals, which is given by this, okay? In where I've written in terms of X plus coordinates, there's a corresponding X minus coordinate transformation. But the basic answer is that, well, if I go back up here really quickly, this looks like literally a double integral. So it integrates in an uncorrelated way, point O in let's say L and O in I, and also some terms from O in L and this O also in L and also for I. But what we find is that in the leading small delta L over R limit, so this long distance limit, what we find is that actually there's a single integral and they're correlated. So what you get is that this delta HLI is just an integral of O in L times O at its corresponding point in I times some smearing function. So if this is L and if this is L and this is I, there's an operator here which is an L and there's an operator here which is an I, and what you do is you integrate over the position of O here in I, like you integrate over some trajectory. It actually ends up being a Rindler trajectory. And here there's a corresponding trajectory of this operator, which you're integrating over. Okay. And these are chiral operators, so you can just think of them as being just functions of this null coordinate.
Sorry, Adam. Just to make sure I understand the notation well. So what you call delta HLI is the modular operator, modular Hamiltonian for the 2 region in an excited state that was perturbatively close to vacuum.
No, sorry. These are all vacuum. These are all so remember, I'm trying to compute this quantity here. So I'm trying to compute the expectation. This is the ultimate goal, is this expectation value of the vacuum modular Hamiltonian in the excited state. So these deltas are all vacuum. These are all vacuum deltas.
Why is there phi then? Why is there? Yeah, can you scroll down then? I'm a little confused.
Yes.
Yeah, further down. What is O here?
Oh, I'm sorry. Thank you. I didn't explain this. So the answer, so we have some theory, okay? We're trying to compute HLI. What you would expect is that to leading order in N, the contributions to HLI are given by the lowest dimension operators in your theory, okay? They should be the dominant contributions to this. In particular, in this small delta L over R limit, the leading piece in this expansion, you can expand, this thing will have terms that are higher order in delta L over R, but the leading thing should be set by the dimensions of these operators. So the leading term here is going to be lightest operator in your theory.
This is this is just because the first correction to the clustering of the four twists.
Yes.
I see.
Exactly. That's exactly right. I'm sorry, I totally didn't say that. So there are terms. This is a bilocal operator, and these O's here are the lightest operator in your spectrum. So it's dominated by the lightest operator in your theory. Sorry. Thank you. Okay. So this is the answer. This function here is not actually important. We compute it explicitly in the paper, but for the purpose of this talk, it's just some smearing function, which has nice transformation properties. So.
Sorry, can I ask another stupid question? So this is probably very obvious, but I just want to make sure that I'm not missing anything. So what you have is you're not calculating a 4-point function, you're calculating a 4-point OPE, because this is the operator state. You're trying to get an operator.
So the way we compute this is, I should say, the way that we end up computing this this modular Hamiltonian is that we take what we do is we compute delta HLI, or really HLI. We compute HLI in an excited state via a replica trick. So what we do is we can compute this by writing trace of sigma, trace of rho psi, which is the excited density matrix, sigma omega to the n-1, limit as n goes to 1 of this quantity, okay? And we strip off the leading order in n-1 piece of this. So this quantity here, we compute at integer n via a twist operator insertions. And then we take the limit where the twist operators associated with this guy are approaching each other, and we take the OP of twist operators. So this can be computed by inserting by a path integral where we have twist operators at the endpoints of all the intervals. And two of the twist operators in the small I limit are approaching each other. So we can take the OPE and expand. And the leading contribution to that OP will be the lightest operator in your.
Yeah, I guess that's exactly the question. So why is there no O term? Why is it always bilocal?
Yeah. Beautiful, because so when you have these twist operators, so when we work in the replicated theory, so we have a twist operator sigma sub minus n and sigma sub n, let's say, for twist. These sigmas are the twist operators. One is here and one is, so this is an anti-twist operator on the left and a twist operator on the right. And what you're looking for is the OP coefficient between these guys and, say, an operator and a single operator insertion. Okay. So this thing should be proportional to that OP coefficient.
No, but don't you have two more twists?
No, I'm just fusing two of the twist operators, right? So I'm looking at the OP between
sure.
sigma minus n, sigma n.
Sure.
The OP coefficient in that OP, I just need to compute this 3-point function, right? But this 3-point function can be computed explicitly by mapping to hyperbolic space. And then you just have a 1-point function. Effectively, this is set by conformal symmetry to be 0, because this is proportional to a vacuum 1-point function.
I see. Yeah, thank you.
So the leading thing is actually a multi-replica operator. So an operator which is in, or what we call a multi-replica operator, which is in one operator in one replica, another one in another replica, and then like this. So this operator you should think of as it kind of looks like a 4-point function, but it's really a 3-point function in the replicated theory. Where this is thought of as a single primary operator in the replicated theory. And so this is the first correction. So that's why you get these bilocal operators. Sorry, that may have been a bit technical for some people, but yeah, that's okay. So the upshot is that the leading correction is this bilocal operator. And so now we just want to take this and plug it into that correlation function. So what we had was this, we're trying to compute this QNet correlator. We can write this in terms of the density matrices, use Baker-Campbell-Hausdorff, and use this delta HLI formula. And for simplicity, one thing I should mention is that we're going to imagine that we're working in a theory in the bulk, which has a large number K of these light fields. So there's some flavor index which runs from 1 up to K, which introduces a large number of fields. The reason we want to do that is just that as you move the insertion back in time more and more, eventually its boost energy gets to a point where it can start back reacting on the geometry. If you move it too far back in time, it can sort of destroy the quantum or significantly change the position of the quantum extremal surface. You leave the probe limit. But if we introduce a large number K of these fields, we can move the quantum extremal surface out enough such that you don't have to move so far back in time to see the transition from the particle being in the entanglement wedge and out of the entanglement wedge. So we're just going to do this by hand. You can ask whether this is a physically reasonable, I mean, if there are any models that actually have such features, but for now, let's just illustrate. We're just trying to illustrate the phenomenon. We're just going to put this in by hand. This is similar to what was done in this work of Maldacena, Stanford, and Yang, this diving into traversable wormholes paper where they assumed they had a large number of light fields.
Sorry, don't you need K to scale with N?
No, we do not need K to scale with N. We just need K to be much, much less than, much greater than 1 and much less than G Newton.
Okay, thank you.
Although I should comment that you don't need that, but in 2 dimensions, you can actually come up with examples that actually have that feature, that K scales in some way with N.
Thanks.
So, okay, so we have this formula, this bilocal formula for delta HLI, and we plug it into this correlation function here. Okay. So what we get is this after doing that. I'm being very schematic with my notation, but I'm just writing this as O left, O right, but you should imagine that there's some integral, like what we discussed earlier from the modular Hamiltonian. Okay, so now you need to compute this. All right, the good news is that this has basically been computed before. So how do you compute it? The way you compute it is you rewrite, or you think of this correlation function as describing a scattering amplitude for a scattering process in the bulk. So what is the scattering process? So there are these O left, O right guys, and there's this phi right, phi left. So the scattering process is that I send in down here, I send in a particle phi right, way in the past, and then there's an O left, which I also send in, and then they collide. It doesn't look like, just because of the frame that I picked to draw this picture, it doesn't look like this is sort of good kinematics for a scattering amplitude, but you can pick an equivalent frame where this O left is far down in the past and phi right is still far down in the past, and then they collide, and then they could come out, right? And you're measuring the probability that they collide, and then phi right makes it out to phi left, and O left makes it out to O right. So this is the subject of, this is the type of thing that's computed in studies of quantum chaos and out-of-time order correlators. And you need to pick, so in this limit where we're taking T right large and negative, so T right much, much less than 0, you're entering what's called the iconal limit, and the scattering phase is a particular form. And this is where we will introduce our stringy, so-called stringy corrections. So in gravity, the phase takes this form, but with this exponent j set to 2. This j, I'm calling it j because you should think of it as the spin of the field that's mediating the interaction. So these fields are scattering off each other through exchanges of gravitons. And the spin of the field there is 2. So this scattering phase goes like the center of mass energy of the collision to the power j minus 1. So in this case, it's just linear in the center of mass energy in gravity, okay? And in string theory, in higher dimensions, what happens is you can sort of think of it as this exponent being modified. So the reason this happens is because now these two particles can exchange more than just the graviton. They can exchange all of the sort of the lightest string modes, the leading redshift trajectory of modes of the string. And when you account for the effect of all of those modes together, what it does is shifts this exponent. It has the effect of shifting this exponent below 2. So this exponent is directly related to the Lyapunov exponent in the boundary theory. So for a theory when j equals 2, the boundary Lyapunov exponent is maximal. It saturates the so-called chaos bound, which says that this exponent here can never be greater than 2. But when j is strictly less than 2, well, you can get different behavior. Okay, so this is where we've sort of inputted all of the so-called stringy corrections. So the picture here is that we're throwing a string at this quantum extremal surface, and we're sort of scattering it off of the quantum extremal surface. Okay. So now, given this, you can kind of run through all the steps. These steps are basically just copied from Maldacena, Stanford, and Yang. You expand these excitations, which I inserted on the boundary, in terms of their momenta, in terms of some momentum basis, and then you couple them with this scattering phase. You try and do these integrals. They're a bit of a pain, but what you end up with is the following: that our correlation function f, which we want to compute, is some integral against the momentum wave functions times some exponential of the momentum raised to some power. And all of the s dependence of this, the modular flow, this s, all of the s dependence is in this coefficient here in the exponential. And this coefficient here is a function of j and s, and it's actually sort of difficult to compute, but it needs to have certain special properties. And those properties we can check, and I'll explain those now. So the properties are the following. When j equals 2, this function here, h sub 2, needs to just be entire in e to the s. It's just e to the s minus 1. So this is related to, the appearance of this e to the s minus 1 is related to this work by Sahan and Faulkner. And it's happening because, so let's plug this in. So if we take this and we plug it in up here, j equals 2 just corresponds to a linear in P. So this looks like, when j equals 2, this whole thing looks like e to the I P plus times some delta xq times e to the s minus 1. So what is that? What that's doing when you insert it over here is it's just shifting phi right by an amount proportional to delta xq e to the s minus 1. So this is good. We needed to see this because actually this was computed, a correlation function like this was computed, we computed it with Arvind Shabazzi-Moghadam and Ronak Sunny in a paper that came out this summer. And the reason this shift is happening is because when you throw in this particle phi right, the modular flow that is included in this correlation function produces some shock. It's producing a shock at the quantum extremal surface or near the quantum extremal surface. Actually, to leading order in perturbation theory, in this small parameter, in the small width of this interval, you can't tell the difference between whether the shock is at the quantum extremal surface or at the horizon. But so there's a shock there, and you're scattering this probe particle off of this shock. And the shift due to the shock is precisely proportional to the position of the quantum extremal surface times e to the s minus 1. Okay, so in the large negative s limit, this thing just limits to minus delta xq. And so the shift is actually enough to just move this particle. Say you threw it in exactly null separated from the quantum extremal surface, it just shifts it down to the horizon at large s, okay? For j, so that's the story in gravity. So there's just this simple behavior in s. For a stringy theory, for j less than 2, this thing still grows exponentially in s at large positive s, and it grows with a smaller Lyapunov exponent. But it's a much more complicated function of s. part of the reason why it's so complicated is because it needs to obey. So your first guess might have been e to some nice formula like this, that h just goes like this. That can't be true. A formula like this cannot be true because there's a reality condition on h sub j, which is imposed by the requirement, well, basically because this correlation function, one can prove, needs to be real along this imaginary line in the S-plane. If you're interested in that, I can explain why that is, but just trust me that there's a reality condition which is imposed by causality. Basically, this is the reality condition that our correlation function down here needs to be real along this complex S line. And basically, the complex structure of this function is such that that works out. And you can see that this ansatz, this guess here, does not obey that. If you move s up to I pi, this quantity here is not real for j less than 2. Yes, sorry.
How much more time do you need?
Give me 5 minutes.
Sure.
Is that okay?
Sure.
Okay, great. So, all right. So we've computed this correlation function in the Regge limit, and now we just need to take S derivatives. And this is the sort of the main result. So we take this S derivative, and we produce this expectation value of the full modular energy. And it has this interesting behavior as a function of t right and the smearing length delta. So what is the interesting behavior? Well, it's 1 minus this exponentially growing piece, but as a function of j, it has this interesting dependence on delta. Namely, when j equals 2, so let's analyze this formula when j equals 2. So when j equals 2, what you find is that this modular energy, which is the difference in the relative entropies, goes negative precisely when the excitation crosses it becomes null separated from the quantum extremal surface. So you can compute this delta x here, and it goes from being positive to negative right when the excitation is crossing the quantum extremal surface. For j less than 2, note that for j equals 2, this delta dependence in the time when this, so when this thing goes negative is when this overcomes the 1 here. When j equals 2, this delta dependence is absent. But when j is less than 2, there's a delta dependence here. So in other words, when delta is small, this is a positive exponent, right? So when delta is small, this thing actually you need to go to larger times to actually get the particle out or to make this quantity negative. So as you try and smear the particle less and less, it takes longer for the excitation to leave the entanglement wedge. And it's also moving at a slower rate, or it's growing at a slower exponential rate. All right, just for the interest of time, I'm going to skip over a lot of this, but one thing that I should say is that the position, the shift in when j is less than 2, the position of the transition between the particle being in the wedge and out of the wedge looks like it obeys a modified quantum extremal surface equation, where instead of taking derivatives with respect to the derivatives of the generalized entropy with respect to the position of the surface. So remember, to find the quantum extremal surface, you need to extremize this generalized entropy. For j less than 2, it looks like there's some sort of fractional derivative equation that the position obeys, where the derivative, the fraction of the derivative set by the Lyapunov exponent. I'll just say that. All right, so I'm gonna skip most of the details of this, but this slide is basically just explaining. So we've computed this simpler quantity. We found some interesting qualitative behavior, and now we would like to compute. We want to go back to the quantum fidelity, which was this more difficult thing to compute, but is the more relevant quantity. This is basically just a slide explaining the perturbation theory. So there was this formula for the relative entropy, which I wrote briefly, which was like trace of square root of square root of rho sigma square root of rho. And you can expand this quantity in rho close to sigma as such, and you can get some formula. So this is some formula which involves modular flow for these regions little r. Anyway, using the techniques that I discussed, you can actually compute this integral over modular flow here, and this is what you get. So what I'm plotting here is a function of t right. So this is for j equals 2 as a function of t right. So t right is the x-axis here. I've plotted the fidelity susceptibility. So this is 1 minus f, and I've normalized it. I've normalized it by its value at infinity. So the fidelity susceptibility is not actually bounded between 0 and 1 because it's a second derivative, but it does have some positivity properties. So I've just normalized so that it goes to 1 at infinity. So what happens in gravity? You move back in time, right? So this is positive t right. So we want to move the excitation back in time. So just to have the picture in your mind. You move the excitation back in time. So here's my excitation. I'm throwing it in at some time t right. So as it becomes more and more negative, I've normalized it so that in this plot, t right equals 0 is when it becomes null separated from the quantum extremal surface. So in gravity, you can see that the fidelity drops, well, the 1 minus the fidelity drops to 0 pretty sharply. It's a very well-defined transition. And this is for various delta. So it's sharpest when delta is closest to 0. That makes sense because it's very well localized, the particle. So you're sort of imaging the quantum extremal surface at the highest resolution at higher resolution for smaller delta. But now if we look at j equals, let's say 3/2, right? So this is strictly less than 2. Now there's this interesting behavior. Well, what happens? First of all, you note you should compare the blue to the blue. What happens is that the excitation takes longer for it to transition into the other wedge. And furthermore, as you try and localize delta, you see this logarithmic behavior that I was discussing earlier, where as you try and localize delta, it takes longer and longer for the excitation to leave the wedge. Whereas when you localize delta here, it always transitioned at roughly the same time. Okay. So we're clearly seeing the same kind of behavior as we saw in the difference in the relative entries in this fidelity as well. So what's going on? How should we interpret this smearing out of the transition? So this is my last slide. So the smearing out, well, what we would like to interpret it as is longitudinal string spreading. So this type of effect has been seen before. The basic idea is that in gravity, as you throw a particle in, actually as you move it back in time more and more, it gets length contracted and actually it fits into the entanglement wedge. But in string theory, there are classic papers by Susskind and others, and Silverstein has done a lot of work on this, Eva Silverstein, that as you move the particle back in time, it spreads out. In string theory, the string starts to spread out more and more, okay? And these two counteracting effects actually sort of cancel each other out, and the string spreads to some size along the t equals 0. You should think of it as on this t equals 0 slice, the string spreads to some size, and we're sort of sensing that. I can discuss why this maybe is not. So one way you might want to interpret this is as a change in the nature of the quantum extremal surface itself in string theory. We can discuss why maybe that's right or wrong, but the point is that one or the other is happening here, and we're sensing this change. Either the quantum extremal surface is changing, or the string itself is spreading out. And that's sort of the last. Sorry, here I had some picture that I was going to describe, but that's the last thing I had to say. Yeah. So
thanks so much. Thanks so much, Adam, for the great talk. Are there any questions?
I have a question. I don't know whether this question is meaningful or not. Are you assuming entanglement wedge nesting, or do you see that condition from the calculation by looking at the scattering phase?
We see it. We see it explicitly. Yeah, you can compute. You can. So the fact that the entanglement wedge is nesting is just the fact that this, well, it's related to the fact that this shift here is positive. Sorry, excuse me. This delta x here is positive.
Okay.
Yeah, so you see it explicitly.
Okay, thank you.
Are there any other questions? If not, I have one last question.
Yeah.
So the usual set of words that are said for the chaos bound is that you have a small parameter that you're expanding the other time order correlator in.
Yeah.
And it could be h bar, it could be n. So n is the one that we usually talk about when we're talking about theories that are maximally chaotic, such as SYK or JT or SYK, right?
Yeah.
So here in this modular, I guess, chaos story you're telling, what is that large parameter? Are you also taking to be large N?
Yes. So sorry, I should say that this quantity here. Sorry, this slide is a bit of a mess. Hang on. Sorry, this quantity here is order G Newton. So there's a G Newton in here that shows up because the scattering phase has this G Newton in it.
So yeah, okay. So it is the same story as usual that you're doing a 1/n expansion.
Yeah. Mm-hmm.
I see. And then the coefficient of the 1/n expansion has this delta to the power of 2 minus j dependence. That was key here, right?
Yeah, that's a new phenomenon. Well, I think other people would have seen it if they had analyzed the correlation function in a similar way. But yeah, that seems to be a key phenomenon here.
Thank you so much.
That there's this time scale at which this quantity here, this log delta, transitions from being positive to negative, depends way more on features of what you're actually throwing in. So, for example, how much you smear it in time, what its dimension is. So I didn't say this, but the dimension of the probe particle phi, this delta x here, for j equals 2, the dimension on that probe particle drops out of this quantity. So it's that the transition time is independent of the dimension of the particle that you're throwing in. I mean, up to non-probe corrections. But in string theory, that dependence on the dimension actually reappears. So it's string theory is much more dependent on what you're. Yeah, I interpret this as saying that string theory is much more dependent on what you're actually using to probe the space.
Well, thank you so much. Are there any last questions for Adam? If not, let's thank Adam again for the great talk. Thank you so much for giving the talk.
Yeah, thanks for having me.
All right. Bye, guys.
Bye.
Thank you.